if my stuff wants to work. All right, so the first thing we went over this semester is elimination and E1 versus E2. So what I would do is on your note card, put on like what we know about both. So E1 starts with a leaving group and ends up with a double bond where the leaving group was, or adjacent. We also know that it takes place with a weak neutral nucleophile, and the leaving group for it is always going to be tertiary or secondary. Another good thing that we want to know to recognize this mechanism is that we are going to be doing it with heat. We have a strong leaving group, so some examples of that are OTS is one, iodine is another. So our strong leaving groups. This is also going to be done with a polar protic solvent, which means that the solvent that we're using is going to be something that participates in hydrogen bonding as a donor and an acceptor. As far as the mechanism for this goes, it's going to be a few steps. So the first one is we might have to do it. So it's going to be in red. It's going to be making a better leaving group. Then 2 is going to be heterolysis of leaving group. If we have a good leaving group, it'll just leave on its own. Then our third one, and that one's always going to happen, so I'll put it in black. The third one we have to look for is the possible rearrangement step. And then we'll go over the 3 types of rearrangement. They are a hydride shift, a methyl shift, or a ring expansion. The fourth one, or the fourth possible step that will always happen is I like to call it coordination to the H. And also at the same time, we're getting formation of the pi bond. So that's our mechanism. I would recommend throwing that on a note card that you'll have for it, just in case you forget. Like, I can recognize, all right, I'm doing E1, here's what we know about E1, and here's what we're going to do with it. And then E1, just the definition of elimination, and I'll put that up here as well, is, or just kind of what we're looking for, is starting with a leaving group and ending with a pi bond. Okay, so let's do a few examples of E1. So we'll go with one like this. So if you see like H3O plus or hydronium ion written out like that on an exam, just know it's still H3O plus the way I just wrote it. It's just a different way of saying it. I'm just emphasizing the bond that's there. So here what's going to happen is we are going through our mechanism. I meant to put also delta can indicate heat. Other ones are HV, that is specifically like light or that kind of heat that will do it. You could also see very rarely HT, maybe T control. All these are possibilities. Probably you're just going to see either like delta is your most common, or you could see like 50 degrees Celsius. That's also going to indicate heat. Any of those, just know, all right, we're doing heat. We have heat, so we're doing elimination. Almost always, as soon as you see heat, just start thinking in your head, are we doing elimination? So we also are looking at our stuff, and we kind of go, we can kind of look through our chart of what we know about elimination. We have a secondary carbon here. So that works with E1. We want to compare and contrast to E2 though. And I look at this and no, we're not doing that is because we don't have a strong anion. We have a weak neutral base. We don't have a strong leaving group, so we're going to have to kind of figure out how to deal with that. And I didn't give a solvent in this, but you could use H2O as a solvent in this because we're making that in our first step. And that will act as a polar product solvent for this. Yeah, so the way this works is then we just kind of look at our mechanism. One, we have to make a better leaving group because we don't have one here. So what will happen is these lone pairs on the hydrogen will come, or I'm sorry, on the oxygen will come and take the H off of the hydronium ion, and then the electrons from that bond will be put back onto the ion to make it water. Then what you're left with is a new structure that has the H3O. Now we had OH and now we have OH2. But we know because water is in that second section, it's in row 7, or I'm sorry, row 6A, it means that it's going to be -2 charged typically. So we want it to have 2 bonds to even that out. Here, I have 1 for the hydrogen here, 2 for the hydrogen here, and then a third one connecting. So that this is not stable. It has too many bonds, so it's going to be a positive. And that's not stable. So it will do is now we have a very good leaving group. So it will actually leave. And then we end up with a carbocation on where that leaving group was, just like we typically see. The next thing to look for is there a space in this that is going to be better suited for this carbocation? Carbocation stability increases with number of substituted bonds. So for instance, we want carbocations on primary the least, secondary is better, tertiary is best. And the other thing that is going to deal with stability is resonance. So if I have a bond here, you will probably see this on the ACS, probably not on the term end exam coming up. But you can talk about stability of carbocations. If this carbocation has the ability to resonate onto this bond, and then you'll get this instead. So if I have like a double bond here, this structure here is very stable because that carbocation is able to be stabilized via resonance. Here though, in our example problem that we were just dealing with though, we didn't have that double bond there. So we're just going to look adjacently. Is there a more stable place for this carbocation? So, and it has to be adjacent. We can't move more than one. So if I come over here, I look at this one is primary. Currently, I'm on a secondary carbon. And the one next to it, the other adjacent one is also secondary. So And this one is technically a slightly more substituted because it's closer to this tertiary carbon over here, but I can't move to that one because this one is too far. It has to be adjacent carbons. So I could do a hydride shift to move this carbocation onto this one, but it's just not thermodynamically like reasonable to say that because the energy it's going to take to move this to here is not going to be enough for it to warrant the stability. This is not stable enough to be like the movement of that. It's not going to be favored. So what happens is we have made a better leaving group. We've heterolyzed the leaving group. We don't need to rearrange, so we're going to leave that step out. And now we are going to eliminate we'll have coordination of the hydrogen and formation of our pi bond. So we're going to take this water we formed in our first step, that's our nucleophile, and we're going to move it over here. And we have a few options for making our pi bond. There's something called Zaytev's rule that is finding which bond or which pi bond formation is going to be the major product or which one is going to happen the most often. On her exam, she often has a trick question saying like, which products are formed. You really want to be careful to look for it saying which major product is formed. Because in this, you'll see in a second, we're forming a product either way, but we want to form the major product. So just be careful of that. So in this structure, we are going to have coordination to a hydrogen. It has to be adjacent. So we have two options here. We can use this hydrogen over here. We're one of the two. Or on this side, we also have hydrogens. So we are deciding which one is going to be better, this one on the left or this one over here. But we kind of already looked at these options, determined this is primary and this is secondary. So it's going to follow Zaytev's rule to form that product on this to make a pi bond here compared to over here, because this pi bond in the molecule is going to be more stable than making a terminal pi bond. So we're going to use one of these hydrogens and not one of these. And also there's three over here, my bad. So what will happen is this H2O, the O has 2 electrons on it or 2 lone pairs, and it's going to grab the H, and then the electrons in this bond between the H and the carbon are going to make a pi bond. And now when we draw a new product, this carbon that was deficient because it only had 3 bonds and carbon wants 4, it has 1 hydrogen, and we eliminated the leaving group. Now it will have 3 bonds again, and it will be stable. So then our product for this is going to be this. And then we have reformed our hydronium ion we started in because this water took this and we got this back. And our water is now going to be in our aqueous solution. The thing you want to be careful with here is, as I kind of just said, this is the major product because it follows Zaytev's rule. I think that's his name. I might be pronouncing it wrong. It starts with a Z though. But we do have more than one option for the product. You could see technically that major product up top and this product, this product is also made. That's our minor product. So both are made, but one, that major product is more stable, so it's going to be formed more % of the time. And that's what Zaytev's rule is, so it's going to be following that rule. The other thing we want to look for is methyl shifts and ring expansions when we're looking for that, but yeah, this is going to be our answer over here. All right, so let's do another one with, so let's go to I'm trying to think. We kind of learned hydride methyl shifts and ring expansions before, so I'm not going to go back over that. If you are interested, you can watch the last video and then kind of look into that. But so I won't be redoing that, but we will have to use that in a few of the steps in some of our practice problems coming up. So I'm just going to go to E2, which is similar. but it has a few different rules. So E2. And then what we know about E2. For one, I know, oh gosh, hold on. I know that it happens with primary, secondary, or, and I'll put an asterisk next to this, whoops, or tertiary carbons. And it can do tertiary, but it must be a bulky base. So it can do tertiary, but it has to be a pretty bulky base to do that. We also know that it's going to be a strong anion nucleophile. Two options for, or three options for a strong anion nucleophile. This is the immediately way that we're always going to distinguish E1, E2, or E1, SN1, or E2, SN2 immediately, every single time. Does it have Na? Does it have K? Or does it have a minus? That's it. Every single time we're looking for that strong anion. All three of those are going to produce strong anion. Immediately look for that, Na, K, or minus. Those are the only three ways that you'll ever really be indicating that. You could get organolithium or Grignard's reagent to produce a carbanion again, but that was on your last exam. Like this class doesn't like this exam is going to be on this new material we learned, but organic chemistry like builds on itself, so you will still see stuff that you learned last semester, especially in synthesis. So strong anion nucleophile, it must remove an anti hydrogen. It has to be every single time. It has to remove an anti-hydrogen. That's something we can't really like. We want to follow Zeta's rule and get the more subbed one, but if we're doing this, it has to be anti. So yeah, it's a like just regular leaving groups. I'll just put LG is pretty good. So all of our halogens except for iodines are a good example of that. So minus iodine. And then also we're using polar aprotic solvents. So examples of that are going to be DMSO, dimethyl sulfoxide, two methyls, and then the sulfur is that bond in the middle. So that's often you'll see that. Diethyl ether is another one. Both of these are going to be solvents you might see. Anything that is just going to be that like polar aprotic solvent, that's also going to indicate E2, SN2. And the last one with that is it's a concerted mechanism. So it's not going to form, we won't have shifting. As far as our mechanism, what we're going to have is I'll do the same thing where some of these steps we don't have to do. But first one is that same make a good leaving group. So that we might have to do that first to make a good leaving group. The second one is like kind of three steps in one. It's because it's a concerted mechanism. So yeah, I'll just write 1 and 2, but it's really 3 steps in one. First one is heterolysis. Second one that's happening at the same time, and actually I read a slash for this. Second one that's happening at the same time is coordination to the anti-hydrogen. And then the third one is the formation of our pi bond. So that's the two things that are really going on here. E2 is pretty like quick, and we're just getting straight to it. So let's do an example of E2. Oh, also real quick though, bulky base examples. I'll just write some. This is called tert butoxide. There's a few ways you could see it. You could see it like that, or just know that this is a strong anion. So you could also see it as Na or K. Both, all three of these ways, it's the same thing. But this side of it is bulky, which means that we're going to end up with a with that. It'll make it less subbed. Actually, I'll throw that in here as well. I'll move this up and throw that in here. So if we are doing that tertiary, or if we're using a bulky base, it's going to be hard for that base to get in at the leaving group and make it that less or that more substituted pi bond, because we're ending up with a lot of steric hindrance when we try to do that. So what we end up with is a anti, I think it's spelled like this. It's anti-Zatev's rule, meaning that we're going anti what it normally should be. So that minor product we produced before over here is now our major product. So if we had a bulky base, we would switch these two. So let's try another one. Let's do an easy one. And then, so this is an obvious example of E2, because we have heat and we have KOH, or potassium hydroxide. We know it's a strong base, so that's a strong anion, meaning that we're going to be doing E2. This is a primary leaving group, and it's a pretty good leaving group, Br. It is that electron rich over here, because it's very electronegative, and this one is a very electron poor in turn, because the electrons are being pulled from here in this direction. So here what happens is, I'm gonna erase these so I can draw my arrows. But our lone pairs on oxygen, and we're gonna have 3 because this is a cation, or this is an ionic bond. So our oxygen is actually negative and our potassium is actually positive. What we'll do is come grab this bromine. Oh, I'm sorry. The other thing we have to determine is the hydrogen we're using. We have just one option because this is primary. There's only one double bond we can make. We have a hydrogen here, one here, and one here and here. We're not going to use either of these two because they're on the same carbon as a leaving group, so that just doesn't make sense to do. We can't use these two because they're opposite, and they're the only two we can use. So I like to think about this as bond formation, bond break. So it's going to come grab. I'll make this red actually. Bond formation from the O to the H. Bond formation, and this pi bond formation of the electrons in the HC bond into the new C to C bond is the pi bond, and bond break, which is heterolysis of our bromine leaving group. So those are 3 arrows. It has E2 has 3 distinct ones: bond formation, bond break, and that makes a pretty simple product. 1, 2, 3, 4. And it makes this terminal alkane. And we can't, there's no other place, there's no minor product in this. We started with a terminal leaving group or a primary leaving group. So there's no other place this double bond could be made. So that's one example. Let's try a second one. And this time we're going to make it a little bit trickier. And then we use sodium methoxide. Same thing here. No, I'm sorry. Actually, we're not going to use heat in this. What we use instead is this conjugate base. This is the conjugate acid of it. Typically, Dr. Barrett has been saying like, as long as there's like, she won't give you one that doesn't have heat. But recently, like, she did one in class that didn't say heat. But so just want to indicate, when you have a really strong anion like this, and you have as your nucleophile the strong anion version, and your solvent is the conjugate acid of that nucleophile, you can still end up with elimination. I doubt you'll see this on the exam. It's possible though. Also, real quick, I'm just going to make sure. Yeah, we're recording. So it's possible. Same steps here. We know this is a strong anion because we have that sodium here. So this is indicating a strong anion, which means that sodium's plus and oxygen's minus, and it has our lone pairs here. Now we want to look for which hydrogen we're using. So we have two options. We know there's one over here. Actually, there's two over here. And then there's one over here. And we know this top one is going to be on a wedge because the methyl group that we have here is on a dash. So the only possible thing that we could have for that this hydrogen is on a wedge. So this one's definitely on a wedge, and that methyl group's on a dash. So we kind of have two options. We want to follow Zaytev's rule and make the more substituted pi bond, but there's a problem with that right here because we want to make this one. But we would have to take a syn hydrogen, which we can't. It has to be an anti-hydrogen to the leaving group. So we have to use one of these instead of using this one. Has to be one of these because we have to take an anti-hydrogen. So this O is going to come grab it, and the electrons in the hydrogen are going to move into the bond, and the bromine is going to leave. So this was bond formation.
I have a question.
What's up?
So you said it would go to the bottom one because it's not, or because that one's anti or whatever.
Yeah.
But isn't the top one tertiary, so it wouldn't go there anyway?
So we still want to make, even with E2, we still want to make the most the most substituted pi bond, but because that's just more stable in general. But just
Okay.
how
Gotcha.
E2 works, it's going to go to the anti one.
Okay.
Yeah.
Thanks.
No problem. But you're right in thinking, like, when you have a carbocation, you want that one to sit on the tertiary carbon. We just need the leaving group to be on secondary or primary. It doesn't matter too much if the hydrogen we're eliminating to be on that. So this will do that anti, and then we'll make our product. And it will be right here. So that's our major product, and we don't have a minor product here because we can't take this one. So I'm going to do another example, but I'm going to wait a while and have you guys do it. And this one is going to be kind of a two-step where you'll have to do both elimination or E1, E and 2. So I'll leave this one for a second and then go ahead and take the time to, if you're watching the video afterwards, just kind of pause it and skip, or if you're here, I'll solve it in like 5 minutes at 3:45. All right, I'm just gonna, it's like a minute early, but this shouldn't take you 5 minutes. So the first step was number one. Sorry, I forgot to put heat in there for a while, but they both should have been heat. And honestly, the heat from the first one typically indicates heat for the second one, but you will probably see them labeled twice. So the first one was E2 because of our strong anion right here, always going to indicate E2. So plus and minus. I would take the time on the exam just to kind of look at your steps and indicate, all right, what are we doing in each one of these? So like if it's a synthesis, go, all right, this is going to be E2. and then keep going. This is going to be E1. What are we doing in each of these steps? This bottom one was a it was a weak neutral base, so that one was E1. So now we look at the molecule and go, okay, I know I'm doing E2 first. So what is that gonna do? Am I gonna do this one or this one? If I had a bulky base, I would take off this tertiary one, but I don't. So I have to take this one for E2. I also probably should have, to make it a little bit harder, thrown in stereochemistry, but you guys were lucky. So what we'll do is we will find our hydrogens adjacent to our leaving group, which there's one here, and there's one on that other side of the carbon. So first thing that we do, we can go back to our list. We know the first step of E2, well, is the check for a good leaving group, and we have one. Bromine's a good leaving group. The second thing we're going to do is just go through our mechanism. So heterolysis of our leaving group, and then coordination, or bond break. Yeah. And then it's one conserved mechanism. So we're going to come and make the bond to that hydrogen. The electrons in it are going to go down, and the bromine's going to come off. This is our major product because in this one, if we use this hydrogen, we're going to form the more substituted bond. This one would be our minor product because we're forming the less substituted product. So after this step, we will end up with the same molecule, but without our leaving group. So and in turn, we have that double bond here, and that's our first step. And the second one is going to be a similar molecule, but this one didn't have sodium, potassium, or a minus charge. So this one was a weak neutral base, and here we're doing E1. So first step in E1 is going to be heterolysis, or first checking leaving group. We don't need to do that. We have a good one, and it's going to leave. And we'll end up with a carbocation. So I'm just going to copy and paste this. And then our carbocation is here. This is the most stable place of the molecule. If I look adjacent, if I go this way, we're primary. If I go this way, we're primary. If I go this way, we're secondary. So I'm not going to move my double bond into any of those places. So moving from here to here is going to give us just a less substituted spot, so we don't have to do that. Now looking for which hydrogen we're going to use, I have 3 options for carbons. There's those ones, and I'm just going to write 1 here. And there's 3 on this one too. But the only one that's going to give me my major product, again, I would have 4 possible products. I could get one going this way. I could get one going this way. I could get one going this way. And before, we also could have had one over here on this double bond right here. But yeah, we're just looking at the major product right now. Here, the major is going to be taking from one of these because it's a secondary carbon and it's going in the direction of more substituted. These are going to make terminal alkenes, and we don't want that. So we're going to grab from these. The other thing that's going to make this so much more favorable is if we go on here, we're going to make something called the conjugated diene. It's pi bond, sigma bond, pi bond. So that's going to make it more stable as well. So we definitely want to go here and use one of these hydrogens for it. So the O's electrons are going to come take one of these hydrogens, the top one or the bottom one. And then we have bond formation, bond formation. And that just gives us this product. So if you had this as your major product, congratulations, you're a winner, and you're gonna go on to succeed in life, probably. So that would be our major. Again, we have a couple minor products. Just have that in the back of your mind for a possible exam question. That's not the only product made, it's just the only major product made. Yeah, So that's E1 and E2. I'll just do one real quick one that has to do with a methyl shift or a ring expansion because we haven't done any so far. And then the end, we'll end up doing some synthesis that does have to do with that. So we'll just do one real quick. We'll do a similar one. I'm gonna do one that's very similar to that last one, but that has just a few differences. So if you want to solve this one real quick, go for it. I'll give you guys 2 minutes to do it. I'll give you to 3:54. All right, welcome back. So this one we're just going to be doing. So the first step is a strong anion. So I think I mentioned earlier, I hope so, that T-but means tert-butyl, or that's potassium tert-butoxide. You could see it in a lot of ways. Just know that it's this and that it's a bulky base. And because it has potassium, it's a strong anion. So what we'll be doing here is finding where we're going to be taking from. So I had mentioned E2 with a bulky base produces the less substituted pi bond, or the anti-Zaytev's rule. Also that it's going to take tertiary because it's too bulky to get in at these other leaving groups. It will take the tertiary one instead. So what we'll do is come grab this, it's gonna be E2, so we're gonna look at the hydrogens that we're gonna grab. We have options again. We have this methyl group. This methyl group's the same. I just don't feel like drawing the hydrogens for that, but there's them there too. But both these groups are the same. Or we could take the secondary one. Again, we're using a bulky base, so we have to take the primary one. So this is going to come, the electrons in this are going to come grab one of the H's. The electrons are going to move in to make our pi bond, and the leaving group's going to leave. So bond formation, bond formation, bond break. So that's going to be our first one. And if you put the double bond over here, it's the same thing. The second thing we're doing is using ethoxide, which Oh, and sorry, we know we were doing E2 for the first step because we have a strong anion and heat, and we know we're doing E1 here because we have a weak neutral base and heat. So here, first step, leaving group leaves, bye-bye bromine. And then we have a carbocation. And now we have to think, is there a more stable adjacent carbon that is, we're on secondary, so that's tertiary or quaternary? And yeah, the answer is yeah. This one over here is tertiary. Should put that in blue. So, and over on the other side, this one's secondary, and then when we're on is secondary. So it doesn't make sense to move this way because we're going to be getting the same thing, but just less thermodynamically favored. And over here, we are getting a more stable carbon. So for sure, we're going to move it over there. But the thing to be careful of is determining whether we're doing a hydrogen shift or a methyl shift. This would be a hydrogen shift because we have a tertiary carbon. So there is a hydride that's available for us to use here, or a hydrogen to use here, my bad. We're only ever going to do a methyl shift if we have a quaternary carbon, or there's 3 methyl groups, or there's 4 total things coming off the central carbon atom, besides hydrogen, obviously. So secondary, tertiary, always going to be hydride shift, and then quaternary is going to be a methyl shift. So how it works is the electrons in the H are going to move over here, and I just like to draw arrows of the carbocation moving over, and then we end up with a similar atom. And now that hydrogen that was over there is now down here. I'll even put the hydrogen before in blue so it's easy to see. So that's what's going to go on there. And then that OH group, this ethoxide is going to come in and finish our elimination. So we're looking for the adjacent most stable carbon. So, or the most, when we're forming the pi bond, we're looking for how we're going to get the most stable pi bond. And we're actually going to use the same hydrogen. It is still important to say that you're doing that methyl shift though, or that hydride shift, because this is going to be more stable here. And the second reason is because you're going to get different minor products. So I'll indicate that in just a second, but this would happen. So this O is going to come grab the hydrogen, and those electrons are going to move up into the bond, and we'll form our product. But again, if you're doing this in the open-ended, you still want to indicate your hydride shift happened, because if you go straight, because if I were to just eliminate here, I'd get the same product. I still want to make this major product of having a double bond here, following Zaytev's rule. But it's important to indicate your hydride shift for 2 reasons. A, I promise you she won't take off points if you do a hydride shift. It's not necessary as long as you're forming the same product. And 2, now we're forming different minor products. Here, this is the major. And the minor, if you went for not, if you went with Zaytev's rule, would be this, as well as your other minor product would be almost the same thing, but a double bond there instead. But if we didn't rearrange, our minor products would be, I'm not going to draw the whole thing, but we could have also formed a double bond here. So our minor product would be this. So that's why it's important to rearrange it. So that's E1 and E2. So the next thing we went over is electric flow condition. So there's two kind of types of electrophilic addition. These aren't real terms, but they're like Dr. Barrett's terms, but it's an easy way of like incorporating like things into like SN1, and E1 is similar to type 1, and SN2, E2 is similar to type 2. So I honestly like her way of categorizing it, but just know that's not a real term. It's just Dr. Barrett's. So E1, oh, sorry, type 1, follows some of the same rules. And electrophilic addition is just going to be going from a pi bond to a like adding something to, and it's typically like some sort of leaving group, not always, but to a new substituent. So type 1, so like you'll start with a double bond and we're adding something on. So type 1 is going to be what we know is that it is often an acid. So HBr, hydrobromic acid, hydrochloric acid, HI. I don't know what the name of that is, but any of those, like often acids, or anything's like H and then some other form of thing that we can add on to it. You could even do like H, you could even, yeah, like hydrochloric or methoxide, you could probably do. Yeah, no, you could. So it's often an acid is the first thing. This, if you're trying to find example problems of what type 1 is, there's a few things. These ones are called hydrohalogenation, like is what they're actually called. So if you want to find example problems online, that's what you should look up, hydrohalogenation. And then we'll go through other ones as we get to them. So is our nucleophile. The other things, we're starting with, they go from electron rich to electron poor. And yeah, that's all that I have notes on it. Those are like the two things. The other one you could write is occurs with alkanes, or alkenes, I mean, and alkynes. For our mechanism, it's SN1 like. So we are, we will be adding the H. So I'll be in blue. So in the electrophile here is going to be this H on all these sides. First, the H is going to add, and then we'll have the nucleophile add as well. So coordination, the electrophile is going to go on first, and then second is possible rearrangement. And then third is going to be coordination of our nucleophile. So that's what our steps are going to be. So let's do example. And we're going to be adding, when we add our nucleophile, it'll follow Markovnikov's rule saying that the major product is going to be on the more substituted carbon. So when we make that double bond or that carbocation after we add the electrophile, we're looking at which side of the carbon is going to be more stable. So I have this starting out, and I can get, we'll do HBr. So this is a hydrobromination or hydrohalogenation, but more specifically hydrobromination. And what happens is I'm just going to draw a bond between the H and Br. This is just for emphasis. It's always there, but we want to draw attention that this exists here. So the Br is very electron rich. It's pulling the electrons in this bond here toward itself because Br is very electronegative. So it can suit the lone pairs it has very well because it even has d orbitals. It's that far down on the periodic table. So this is going to be very electron rich, making the hydrogen electron poor. And this poor bond over here is also electron, or this bond over here is also electron rich because it has extra sets of electrons between or in a bond when it only really needs 2, and it has 4 instead. So we have electron rich to electron poor adding. So that means that the electrons in this bond are going to go over to the H, and the electrons in this bond are going to go into the Br, which will give us a fully negative bromine. Now we have to decide which atom did the H add on to, the hydrogen add on to, not where we're going to put the carbocation, but where did the hydrogen go? We can either put it over here because we're picking a side. And we want to put the hydrogen on the less substituted carbon, the hydrogen on the less substituted, because that will make the other side deficient. So in this example, we're going to put the H on this one because this side is less stable or less substituted than this side. Now, if I look back at my original structure, this bond has 3. This atom has 3 bonds. We have 1 methyl group up here, and then 1 to this secondary carbon, and then also our double bond. So this one had 3 bonds. I look at, and then on the other side, this one had 4 bonds. The methyl, the second methyl, the 1 to this carbon, and then it's with a pi bond. So that's 4. Now this one still has 1, 2, 3, and there's also a second hydrogen here. We just didn't put it on. But now this other carbon has 1, 2, 3 bonds, and before I had 4. So this one's deficient. And we want to put that carbocation on the more substituted side. So in this case, it's going to be here. The last step is just to add, we don't have to rearrange because these are both primary, this is secondary, and we're on tertiary. So we're as good as we're going to get. And the bromine is going to add on where that plus is. That is our coordination of the nucleophile step. And then we'll just head straight to our product. I like to think about that as like minus is adding to plus, and then we have our product. And then we just end up with the product with the bromine here. And that is what we get. The thing that we have to understand about this is a term called regiochemistry. It just means that this is major over the other way we could do it. And I'm sorry, this is a hydrogen. That's the major product. Our minor product in this case is if the bromine had added on the other side. So if we had added the hydrogen on this side instead and placed the bromine over here instead, this would be our minor product. All right. So that's type 1 addition. Type 2 is going to be a little bit different. Mm, all right. So the things that we know in this one is the solvent can really impact what our major product is. So typically we're not super worried. We have like, I don't know, a diethyl ether or something, and it really has no effect on what we got. Or even if you have water, it's not going to affect what we got. And this top one, it's not really going to matter. We have our, I mean, the acid, the HBr is going to be our solvent anyway. We don't need one for that. But yeah, that it won't super matter. Type 2, it really will, because there's a point where we have to identify which one of them is a better nucleophile to add onto our carbocation or add onto our structure. So in this one, I'll write our mechanism as well. The first one is that like back and forth that you saw in class of the one of them. So I'll say coordination of electrophile. That will always happen. And then second is going to be, I'll quote Dr. Barrett, SN2 like arrows. And that's everything. So let's do an example. So we can have this. Oh, one other thing that I forgot to put on here is that it's an anti-addition. So whichever side the first one adds on to is going to be anti the second one. So it kind of produces a racemic mixture, but not really, because they're not really stereocenter. So we have to, or they're not guaranteed to be stereocenter. So we have to be careful saying that. So first thing that we do, or hold on, I'll write out a product. This would be listed as BR2. However, I'm drawing like this for emphasis. So when we look at these are both very electronegative, but those electrons move around. So there is going to be one specific moment where one of them is more electron rich than the other one. And that's going to be the moment that this first step in this mechanism happens. So what happens is this comes in and we have addition on here, and then this one kind of goes back and we make that a 3-membered ring. So we have our same beginning structure, but now we also have this bromine coming off of it. After that, so bromine wants 2 bonds. It is it's in row 7A of the periodic table, which means it's -1, so it wants 1 bond. Here I have 1, 2, so it's not very happy and it's positive. So what will happen is our second bromine, which received the electrons in the last step, is now fully negative. Sorry, I try to do these in red, but sometimes I forget. Well, that looks weird, but we're gonna leave it. The second one is gonna come in anti the other bromine to add on and do it. So this is SN, it's very similar to SN2, where there's SN2 like arrows, where this is gonna come in, where the bromine that's coming in the second time, and it's very important, it's very specific to, this is just for hydrohalogenation, is gonna come in on that, and also if we have it the other way, but yeah, typically this would come in SN2 except for in oxymercurization, which is that one with the mercury step and everything. But yeah, so this will add in and it will send that the electrons back up to the bromine, and this new bromine is going to be coming on. This is where we get the anti of this. It's too sterically hindered to add this bromine up on the top. So this one is always going to come on the back side of it and push the bromine up top, so that this one will be on the opposite side of this one. So when we write our product, BR, and we have another one over here. Just so happens that both of these, okay, one of these is a stereocenter. This bottom one is, because I have this whole group and then this methyl, and there's also a hydrogen here. This one's not, there's 2 methyl groups, which are the exact same, so that one is not a stereocenter. But we want to indicate that this one is anti this. So we could kind of do this. Br on the bottom and the hydrogen in the back. The important thing is these 2 are anti each other. And you could even draw a second one indicating this doesn't matter here because this isn't a stereocenter, but we just want to make sure we're grasping the concept that this could also be the case. I would try to not write plus enantiomer when you're doing this, because they're not enantiomers, almost never. Like for instance, if both of these were a stereocenter, then we would have diastamers, a mixture of diastamers. So because this one is not a stereocenter, we do have plus enantiomer because these 2 are enantiomers of each other. But it's also going to be kind of weird because this is not a stereocenter. This bromine can kind of move. This one can kind of move. But I would just write both products and you'll be safe. So that's SN2, but I mean, sorry, type 2. But you got to be careful because sometimes you get a little bit of not the perfect situation. So you can have this same thing, but with a solvent like water. Same steps are the same at first. This bromine is gonna take, and then another bond's making it to make our 3-membered ring. I'm even just gonna copy this. I did add a bond on the right side of this because I wanted both of them to be stereocenters. But now what we're looking at is Br minus and OH2. Does anybody know which one of those is a better nucleophile? And I have horrible luck when I ask people questions on Zoom, so I'm just gonna go straight to the answer. It's the OH2. So yeah, H2O is a better nucleophile than Br. It's in a better spot on the periodic table for nucleophilicity. So instead of adding this Br, we're actually going to add the OH2. So same thing here though. So yeah, the point is just be careful when you're assessing which one is going to go on if you have a solvent. Same thing happens here though. It adds more subbed. And then actually, I'm not sure whether it goes more sub or not. Let me just take a quick peek in my notes. So the OH is going to go to the more sub side. So when you have, so it's SN2 like when we're doing it with two minuses, this one will go on the opposite side. It'll go to the more stable, which makes sense because it's kind of like SN1 where we want to add it most stable. So like if we look at it in like SN1 thing, if we're thinking about it as an SN1, I have a weak neutral base. So we're gonna go, and then I also have a good leaving group. So like if I were to think about it that way, I would have heterolysis here, and then you would end up with that intermediate. This one doesn't have an intermediate though, but yeah, it's gonna be SN1 like to get it like this. And we're still gonna produce the anti-products. You're gonna end up with water in this. Then your BR is gonna grab one of them. By this point, you should be pretty familiar with protonation, so I'm gonna skip that. And you'll end up with OH. So these two are anti, like I said. Now we do have two stereocenters. So it is really important not to just say plus enantiomer because these are a mixture of diastamers. So I could say that is one answer. And then this would be the other. And I'm just going to choose a random one to make the other side of the stereocenter. So that would be our answer. Yep. So that's type 2 addition. The other thing that you can have with type 2, and I didn't do it with an alkyne up here, but when we do it with alkynes, I'll just go back up here for a quick second. When we do it with an alkyne, or you can just see alkyne, when we do them with alkynes, it's just slightly different. The first thing is we have to look to see if we are told something, or if it says excess. I'm just going to do the same exact one, but with an alkyne. If it says excess, first thing we know is we're doing it twice. So excess or 2. So it's excess, or it could also say 2 equivalents. So same thing, this adds and this moves. We then get the carbocation here, and we add the BR. and get this. And then we have two equivalents here. So we're actually able to do it twice. The problem here though, I didn't think about it when I was doing it the first time. This molecule is not possible. This carbon here has 5 bonds, 1, 2, 3, 4, 5. So you just can't have one of those. But it would be the same process. Oh, God. And then you would do it again. And it would go on to the opposite side. I'm not 100% sure. Let me also take a quick glance at my notes. This one, the reason why I'm not sure, this one's a little bit tricky because they are both, like this is a symmetrical molecule. Typically you'll pick the side that is more substituted, but this one's kind of weird because they're both, in this situation, it looks like from my notes, it would add on the other side. So you would do the same thing we just did again, and we would just have that product, but on the opposite side, the bromine would go on the opposite side to kind of keep it symmetrical. But if you had the same thing, but like this was terminal, they would both go on the more sub side. So you could end up, I'll just quickly not go through the mechanism for this. That would be your product. If one side is obviously more substituted than the other, that's what's going to happen instead. All right. Let's do well, let's do one more that's similar to this one. But we'll do an alkyne with this one because we can also have a surprise product with something like this. Again, I did it again. That one isn't possible. And this here, I'll use chlorine instead. This can happen more than with just Br. So same thing happens here. Where we make our 3-membered ring. And then we have our water. Again, it's a better nucleophile than the Cl is. So the water is going to add instead. And it would most likely be like, it's going to be, it will either be water, or you could also have it as like OH minus, or like KOH or NaOH. Any of those would be an easier way to do it, but and then this will send the chlorine off. And again, we're going for more sub because that's the way it prefers it. And this is also going to be positive. What you end up with is not just this product of chlorine and not just OH, but with an alkyne, we're going to have tautomerization, where you, in the formation of tautomerization, you're going to end up with removing both, because we had H2O, we're going to remove both. The first one, we're going to proton transfer off using the other Cl. So in this product, we actually have plus Cl, HCl. One of the hydrogens is going to come off that way. The second one is going to come off in the elimination when we form this double bond. You won't need to know the way tautomerization works, the mechanism for it, but know that it occurs and where it will happen. So alkyne with water as a solvent is going to happen, is going to equal tautomerization. So that's type 1 and type 2. The other thing that we have done is our other additions. I'm gonna see if I can move my window around really quick so that I can keep showing my screen, but also see my notes for this. I don't know how, so we're just gonna keep going. So other additions. First one is hydroboration. Honestly, I'm gonna tell you what I did for this exam is, and also the ACS. I'll write out all you will need to know for the other addition section. And then we will, oh yeah, sorry, I just gotta bring it back. I'll write out all the ones that you'll need to know, but just it's carbon to whatever it is. And then I would personally write these on your note card and then also memorize them, put them on flashcards, or if you use Quizlet, do that. Memorize all of them, and then just, I'm seeing this product, because for all of these, you don't need to know any of the mechanisms. You just need to go immediately straight from your reaction to the product. It's going to save you so much time on the exam. I know for my, like when I took the exam, she made it hard enough where we didn't really have time to kind of second guess. A lot of it was like, we didn't have time to do the mechanism. You just had to go straight from our reaction to our product. So what I'll do is I will do what the old learning assistant did from last semester and just write down all of the possible things you could do. Just memorize them, throw them on your note card, and then you'll be able to just go straight from that to one to the other. So when you have like carbon, double bond to carbon with permanganate, which is potassium, manganese, and oxygen. And when it's cold, then we get syndials. I'm sorry, antidiols. When you have a triple bonded carbon and cold permanganate, we end up with diketones. And they're typically going to be anti. When we have permanganate, but it's hot, instead of that addition, we're going to get oxidative cleavage. And it's going to cleave this bond into C double bond this oxygen. When we have a carbon-carbon double bond, and we have a X stands for a halogen, but we also have hydrogen peroxide or just peroxide in general. The R groups is the carbon group, then you end up with the anti-Markovnikov addition. When we have carbon to carbon or carbon triple bond to carbon and H2 with palladium, or sorry, platinum or palladium, we get full saturation. When we have, what's another one? Oh, this one's hydroboration, carbon to carbon, and then first you'll see it'll be like this. If you have BH3 and then also peroxide, whoops. Oh yeah, you can do it like that. H2O2 is peroxide, or you can see like HOOH. Then you have anti-Markovnikov addition. So it'll be C, and this one will be an alcohol. And this is anti-Markovnikov due to the peroxide. And same thing up here. This was X1 less subbed because it had the peroxide. What's another one? Oh, if you have two of those, sorry, if you have a triple bond, I mean, here I'm not 100% sure. It's like, I don't know the name of it, but you're still going to make that tautomerization product. Where you get this. And then that's on the less sub as well. Here's an example of ozonolysis. So in this one's a little bit weird to think about. So this is cleavage, but when we have, oh, I'm sorry, that was supposed to be peroxide. But remember, DMS is the only thing that's going to stop this from not completely oxidizing this into a carboxylic acid. We'll do that, and I'll actually do examples of cleavage because I think cleavage is the most tricky. But in this, you will get, like, what will happen is it'll split down the middle and then do O on both sides. And whatever is on both sides of this one, for instance, if this side over here was, let's say they're both terminal. Let's say we're looking at exactly this. This is the bond we had. We're gonna do our cleavage, and on one, actually on both. But you'll get carboxylic acid, so you'll get two of these. Well, let's do it like this. You'll get this. That's what you would get there. Yeah, so if it's, but this one's important. If it's terminal, it's going to be a carboxylic acid. But if we had like this instead, an isopropyl group on the end, now instead of getting a carboxylic acid, we're going to get a ketone. So if it was like that, it would be a ketone. So I had wrote on my flashcards a while ago that it would be, this is the way I wrote it. And I write under this terminal enol to a carboxylic acid. Carboxylic. That's that one. Also, I'll send this note into the group chat so that people can see this whole thing. Again, I would write all of these on a flashcard and then remember it. And then memorize them, or on multiple flashcards. But yeah, also I mean, I like having these just as a remember or as a reminder to have on my like flashcard in the exams. This one's like the same thing, but instead of having the peroxide, we're gonna stop it short with DMS. So remember, if we have DMS, we're gonna have a completely different reaction where we're stopped at just this. So if this was terminal, then we would have like a aldehyde on the end. And if it was secondary, like if it was in the middle, we would end up with a ketone. If we have a secondary alcohol and PCC, we talked about PCC in class. I mean, we talked about all these in class. I'll write it like this, an alcohol like this, or this one's secondary, this one's primary. We end up with either a ketone if it's secondary or a aldehyde. Oh, whoops. Also, so Jones reagents too, so like chromium, but this same thing can happen with like Jones. Instead of having PCC, remember Jones is kind of our one-stop shop. It will do the same thing. So when Jones is, or sorry, Jones isn't, our K-4 is our one-stop shop, but K-4 can do the same thing. So you could use Jones, which is CrO3. And then you could also use K-4 for this. It's going to do the same thing and make a ketone. If that was, I'll do the same thing, or if it was primary, if we are not given DMS, we're going to end up with a carboxylic acid. So, oh, whoops, I'll keep this up here and say the or only DMS stops it from going all the way to carboxylic acid. So this will make a carboxylic acid. And I'll just indicate again up here, that's if it's secondary, and down here, that's if it's primary. This one is, I think it's called oxidative addition. It's OSO4 though. It gives you syndials. I know this is like a lot to remember, but if you throw these on flashcards, you can breeze through getting them down. Last semester, she only called it MCPBA, but she's also using that acid term too. PBA. Does anybody remember, was it acetic acid or?
Did she call it like per acid or something?
Yeah, I think that's what it was.
Per acid. I just looked at my notes. And then it was like, it was per acid or RCOH3.
Yeah, so RCOH3 is just the structural component of it. So yeah, thank you though, it's a per acid. So anything that ends with, and again, R H03. That just means that you have an like an ester that's an alcohol, so, or that's a carboxylic. Then it's an ester with an alcohol at the end. So it would be just, you won't see this on her exam most likely. Again, she changed things slightly since mine, but it would be like this. That's a pair acid, like that OH3 structure, that's this. And sorry, it would be, there's a carbon in there. That just makes a epoxide ring. But I think that she might be telling you that now because she's on the ACS board, or not the board, but she's part of it. So you, she might be telling that because they might be putting on the ACS this year. Who knows? This is an epoxide ring. What else is there? There's only a few. The other two that are a little bit, that are similar to that saturation thing with the hydrogen is, and then I'll put, and this is only done with a triple bond actually. So if you have H2 in Linlards, then you end up with a cis one, and then H2 with dissolving metal, or Na NH3, I think it is. Yeah, NaNH3. Then what you get is for Linlards, it's a cis product, or a cis alkene. Yeah. Man, sorry, my hands are not working. And then for dissolving metal, they're anti. And this one's an anti-saturation. There's a few more. The last two are periodate, and that's it. So when you start with a diol, whoops, and you add periodate, which is HiO4, then you get cleavage as well. So I think that's the honestly like hardest one to remember, that you don't start with, most cleavage is pretty simple. You start with a double bond and end with like them with like either aldehydes or ketones or carboxylic acids. But these ones are weird because you end with you start with alcohols and end up with cleavage. Typically that doesn't happen. So that's the one, and that's all of them. So if you like, I would write all these down. I did write all these down and memorize them all. And then on the exam, you'll be able to see them and just kind of quickly know the answer. Or you can also write it on your note card to have it that way. The last thing I'll do is just do a few, I'll do like cleavage, and then we'll do like one synthesis problem. I'll also do it as a condensed drawing. Whoops. And then we'll do it with DMSO as the solvent. So this one is cleavage of that. You'll see a lot of this on the ACS. You'll probably see something very similar to that on her exam too. First step, draw the line drawing every single time. Like, it's so much easier to do it as a line drawing. So I'm going to do that. It would be I'll do it like this, and then carbon 1, carbon 2. I like to think about it as, okay, how many carbons do I have? 1, 2, 3, 4, 5. And then these two, because it's in that 2, it means it's going to be an isopropyl group. So I'm just going to count it once. So 1, 2, 3, 4, 5, 6. So it's going to be 6 numbered. There's the 6. The longest chain is 6. 1, 2, 3, 4. And then I know here is going to be an isopropyl group, so we'll add that on. And then I also know right before that, I also had a second double bond. So that's my actual thing. Now we just kind of talked about CMNO4 hot will do cleavage. Also, DMSO is not DMS, it's different. It looks similar, but it won't stop it from completely oxidizing. So we'll end up with carboxylic acids on places that are not secondary. So this will also do every single bond in here. So, or every single double bond. So it'll do here. I go straight to the middle, throw an O on both sides, and go, all right, that first one is this, and it has aldehydes on both sides, or it has H's on both sides. That other side of it is going to be this. And because this is not DMS, we're going to go all the way to carboxylic acids. And then I have 1, 2, 3 carbons. One, 2, 3. And then the last one we have is a ketone. And this one's gonna stay a ketone because it has carbons on both sides, and they won't, you'll learn this in Orgo too, but those oxidizing agents won't take off hydrogen or carbons because they're not good leaving groups. And then you can just write plus in between all of them, and that's our answer to that. This will also take off rings too. It'll cut right through the ring, stuff like that. All right, let's do a synthesis, and then we can all have a good night. Oh my gosh. There we go. Yeah. So that'll be first. Just to make, I'll also add this in. Actually, we're gonna change this up slightly. And then I'm trying to think of something as the last one I can do. And give me this a second. I'm gonna add one thing into this. I'll do two actually. So I'm trying to make a really good one. And I want to make sure that it works properly. We'll switch this step out and make it a little bit easier. I want to make sure I put this on here. Yeah, cool. All right, so I'll leave this here. And then I'll come back in at 5:10 or in 6 minutes, and then I'll do it. Good luck. So how'd everybody do? I did realize kind of halfway through that I forgot to take off part of it. You would have done elimination twice, but there was only one leaving group, so it wasn't possible for a little bit there. But this will be the possible part at the end. This one's possible. I'm trying to see if so first one that I think the best way to go through this is to first go, all right, what are we doing in each spot? First one, SN2. I don't have heat, I have a strong anion, SN2. Second one, I have a strong acid, so gonna be elimination and heat. So it's gonna be E1 because it's not a strong anion. I don't have Na, I don't have K, I don't have minus, E1. This one is HBr with peroxide, which means it's gonna be the anti-Markovnikov product. That was just the other additions thing we just did. So this will be EA for electrophilic addition, and then I'll write anti-Mark actually. And then this will be E2 because we are following the because it's a strong anion. This one will be type 1 because it is just HCl type 1. This one will be E2 as well because we have a strong anion and it's a bulky base. So it's going to produce the less subbed one. BH3 H2O2 is going to be that'll make a double bond into an anti-Markovnikov alcohol. So alcohol, anti-Mark. And this will do this last step that we just did up here, right? It'll be this one, and it will go to a carboxylic acid. So I'll do alk to carbox. All right, so that's what the steps do. Let's do them. So this is negative and this is positive because it is a strong anion, and we are going to attack the base and the bromine leaves. This is classic SN2 from before the midterm. And then we get an ether here. E1, we have to make a better leaving group. Oops. Actually, I'll do this. H2OH. This will grab, and this will make it neutral again because it was positive. And then we have this. And then our steps are how to lysis our leaving group. And then our major product is going to take one of the hydrogens over here. So that H2O that we are left with is going to come grab this H, and the bonds here will go up. And then we'll end up with with this. The next step is HBr with H2O2. So it's going to do an anti-Markovnikov product. This was one of those ones that was listed as just a go straight to the product. In that above step, but what will happen is because we are making the anti-Markovnikov product, we'll add the H on this side and the bromine on this side. And then we will do our E2 step with this. So that's going to be taking this one because that will produce the more substituted one. And whoops, this is E2, so bond formation, bond break. And then we will get our product from that again. Right here. And then we have HCl, so that will be type 1 addition. So the first thing we'll do is these electrons will come grab the hydrogen, and then the bond will break, sending the electrons to the chlorine, making it fully negative. Whoops. And then we will get the H on the left sub side and the plus here, but we'll have to do a hydride shift because this isn't on the most substituted carbon. So that'll move, this will move, and we get the same product with our carbocation on the most substituted side. Then our chlorine that we made fully negative in that step before is going to add on to the plus. And we get, this will make an error for me. Yeah. We'll get a chlorine here now. The next step was E2 with a really strong base right here. Even though heat wasn't indicated, we still had that really strong base, so we know we're going to be doing E2 anyway. You will never get substitution where you're adding this on. These will come and take, and also because it's too bulky, we have to do our elimination to the less substituted carbon. So we're going to come take from the top. So bond formation, bond break to get that leaving group where we want it, or to get that pi bond in the less sub spot. And then we get this product. And then we will do the BH3OH. So this is another one of the other additions that we had listed up top. It is just going to be the alcohol. It's just going to make our double bond into alcohol, but on the anti-Markovnikov side. Don't have to do a mechanism for that, just straight to it. And then our last thing is KMNO4 cold. And this is just going to make it into carboxylic acid. And that should have been your product. And sorry, at first I had changed my mind and taken out a step in here, and then I forgot to take it out. But yeah, so that'll be your whole thing. I did just realize I forgot to put deoxymercurization. I forgot to talk about it earlier, but I'll just quickly say right now what it is when you have a double bond and you're given HgOAC, H2O, and the second step you will always be given NaBH4 and OH minus. These will always be together. What just happens is if it's multiple choice, go straight to the product. It is straight to this. where the OH is the more substituted side. How it works is you'll get this in the middle, it'll add, and you'll get HG, and then like AOC on this side, and then there's only one left, and then you'll get the OH comes in, or the H2O, I mean, comes and adds on this side, and this will go up, and then you'll get and then this will first be H2O, and then we'll deprotonate it to be just alcohol. And then this NABH4 step, you don't have to worry about how it happens, but it's just going to completely cleave it. And then you're left with this as your final product. And that's it. Well, this has been our Orgo 2 review session. I hope everybody had such a fun time and loves Orgo just as much as I do. I'll see you guys in class on Tuesday. Study hard. I'm sure all of you guys will do great. Again, I recommend to write all these down on a note card and memorize them. And then, or like on different note cards. And then I also think that you should, like, if you're like me and often like just blank on exams, make sure to write those on your note card too. I would write down all your steps for like what we know and the mechanism for all of them on a note card too, just so you don't forget as well. And the difference between substitution and elimination, which is just always heat. And I think I talked about everything else. So yeah, study hard, guys. Good luck with everything. And I'll see you on Tuesday. Bye.
Thank you. Bye.
Mhm.
Thank you, Dan.
Bye.